And let me get my video started. Sorry. Okay, sorry about that. Sorry to keep you waiting. And I don't know what happened there. Did it? I know. I have to go through my whole thing. Yeah. Yeah. So I'm in the middle of one class finishing up, and then you guys starting. So sorry for the little delay. So we're going to be talking about scientific method. And I had asked, how many of you guys have kids or younger siblings or cousins that you have to watch every once in a while? Anyone? Oh, yes. Okay, good. So in that case, your younger siblings or cousins, they're like the perfect scientists because they're already thinking like scientists. They make an observation, kind of like, why is the sky, or the sky is blue? And then they're going to ask you, or make an observation, they're going to ask you a question. Um, why is the sky blue? And in most cases, what we do is we are like, leave me alone, go play video games or something like that. But in science, we sit there and we go through the steps. So we always make an observation. We start off with that observation. Then we go to okay. So we make that observation, and then we go to establishing a question. So like in that case, why is the sky blue? Then we have hypothesis. Well, the sky is blue because it's water upside down, or something along why we believe the sky is blue. So it's kind of like a guess as to what the answers are going to be. So then we set up experiments, and and then after we do those experiments, we set up our results, we get our results or our analysis, and then we establish a conclusion based upon those results. Now, we look at our conclusion and we see how accurate we are about our hypothesis. If our hypothesis is dead on, then we'll do the experiment again just for validation. But if our hypothesis is off, we'll reestablish that hypothesis, and then we'll go through this procedures again. And then if we get to the conclusion, and if our conclusions were the same as we initially thought they were, then we'll publish it somewhere. Or we'll use it as white papers for a product. And you guys are able to see my screen. Everything is good so far on that side. So, good. Okay. So again, first thing, we're making those observations. Then after those observations, we establish a questions. Then we get to our hypothesis. And then we're going to test it by experimentation. We go through the steps. And then if our hypothesis holds true, then we're going to just verify. We always want to verify. And if it doesn't hold true, then we reestablish our hypothesis based upon the experiments that we did. Now, when the hypothesis has been tested and confirmed by many experiments under different conditions, without any contradictions, we make this a theory. So a theory is when we've gotten to the point where we've confirmed our test, our hypothesis initially, and then it'll be a theory. And then it becomes a theory or a scientific model. Now, today, because our community has grown and science is more readily available for many individuals to do, we often will do a lot of communications. So we do a lot of publications. And And so you'll see a lot of technical literature. And the way that we communicate today in sciences are through those papers, and then also through conferences. And so we will meet and discuss everybody's ideas and their theories, and and we kind of get into those nice heated debates about certain things. you know Now, we also have a law. Now, a law is just going to be a summary of a pattern of regularity that has been detected in nature. And it's going to be something, like I said, it's going to be something that you always see. Then it becomes a law. And then in this case, in the case of a law, you can't have anything that's a known exception. Okay. So chemistry. So chemistry itself is just going to be the study of matter. And so a chemist is always going to be studying matter and the changes that are going to occur from one substance to the other. The chemist is always going to be looking at what's causing those chemical changes, right? And particularly, we look primarily at energy. And so energy, heat, and electrical. So those aspects of it. And then the thing is about chemistry. Chemistry is kind of like the center of a lot of the sciences, right? So chemistry is kind of needed for everything else. So many of you guys are taking this course because you need it for another topic, okay? And we're in every type of industry, from food industries to pharmaceuticals to healthcare. So when we talk about chemistry, we also need to start talking about how we do a lot of our measurements and how we recognize those chemical changes. So when we talk about those measurements, often we're going to have values that are going to be very, very large or very, very small. And as a chemist, we typically are a little bit, we'll say, lazy, right? And okay, so often in chemistry, and in science in general, we use what we call scientific notation because we were going to be working with really large numbers and really small numbers. And we're lazy as all hell. We don't like putting all those zeros, okay? So we have this general form where we have a number, decimal, and then any numbers that follow in it times 10 to, and that E represents the exponent, right? And this makes it a little bit easier. So if we have a really large number, let's say we have something like, 1,000 or 1,252,000. Well, rather than having to write all those zeros and look at my third grade handwriting, what we'll do is we'll just write it as 1.252 times 10 to the 1, 2, 3, 4, 5, 6. So when we look at these numbers, we're going to start where the last zero ends, and then we're just going to count 1, 2, 3, 4, 5, 6. So then that gives us the number for our exponent, okay? So this allows us to do scientific notation. Now, if our number is a very small number, let's say it is 0.00321. So in this case, we're going to start where the decimals at, and we're going to move over 1, 2, 3. So in the case where we have a whole number that is a non-zero number, that's going to be our first number. So then it'll be, oops, sorry about that. It's going to be 3 point, sorry about that. My, again, third grade handwriting. 3.21 times 10. And since this case, the number is a small number, and we're moving this direction. So that's 1, 2, 3. So it'll be 10 to the minus 3. Okay. And so this is, again, it's called scientific notation. The initial form, this form is called decimal notation. So then that way we're taking into account the decimal. Here, we're always making it so we have one whole number followed by numbers following that decimal. Okay. So this is just like an algorithm to help you remember how to do it. We're not going to go into that much. You can look at it later. We're going to go ahead and jump into the problem. Okay, so now what we're going to do is convert the 3.672199 times to scientific notation. And then I also want you guys to convert 0.00461 to scientific notation. Okay, I'm going to let you guys do this, and then we'll come back and I'll show you the process. You guys want to do? You guys have you gotta go ahead. Okay, so now what you're going to do is you're going to take water. You're going to take the water from over there, and then you're going to pour it and bring it up to just slightly. Okay. Who is she talking to? Okay. Okay, good. Okay, so now what we're going to do is just going to move over 1, 2, 3, 4, 5, 6. So our number is going to be 3.672. Now, since these are non-zero numbers, we're going to put them in there as well. 199 times 10 to the 6. Okay. And then down here, we're going to be going in the other direction. That's 1, that's 2, that's 3. So then in that case, it's 4.61 times 10 to the minus 3. Okay. Questions? Any questions? Okay. So why don't we count because we only want a single number, right? So we only want one number and a decimal point. We're trying to make it short and sweet. And then that way we don't have to put all of those zeros there, or in this case, put all these zeros in front. It just makes it easier for us. So we only want a single number, then a decimal. So then that's the reason we don't count the 6 and the 1. Okay? Okay. Okay, let's see. So these are just ways that we kind of help ourselves remember. I always remember if I'm going in one direction and it's like if the number is a big number, we know it's going to be a positive. If it's a small number, it's like 0.00, we know that we're going to have a negative for our exponent. That's how I remember. Okay, so now this one, we're going to convert it to the decimal form. So we're starting from scientific notation and we're going to change it to decimal form. Okay, so I'm going to give you guys a minute to sit there and think about it and to kind of work it out on your paper, and then we'll go over it. I'm surprised you were able to get it all in there.
Oh, trust me, it was like.
Okay, so we're ready? Okay, so now we know that this is to the negative 11. Okay, so in this case, what we're going to do, we're going to be moving it over. That's 1. Well, let's write it down here. So we have 3.49 times 10 to the negative 11. So in this case, we're going to be moving the decimal point, and you guys can see my decimal point. We're going to be moving it over 11 spots. So we're going to go 1, then 2, then 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so our decimal is going to be now put here. And then we're going to put these zeros in front. That's 1. There you go. I always put a 0 in the front. And so then you're going to remove this part here. And you're going to remove our decimal. Okay, so that's going to be our value. Okay, now can you see why it's really cool to use scientific notation rather than having to write down all of these zeros? Okay, and then in this case, we have 5.16 times 10 to the 4th. So in this case, we're going to be moving in this direction. So I'm going to slide this over. I'm just going to get my 5.16. And then I know I'm going to move it 1, 2, 3 spots. And then one more. 4. Okay, so my value is going to be 51,600. Okay. Are there any questions? Okay, good. Now, since we're going to be doing this often with calculators, you're going to have to learn how to use your calculator. There's a couple of YouTube videos. I'll actually put some links to a couple of them to kind of help you with that process. But if you look on your calculator, do you guys have, if you have a calculator readily available, which you should have it because you're going to be doing a lot of calculations, you're going to take a look on your calculator, and your calculator typically has EE or EXP. So these are going to represent your exponent. So they're going to actually represent, in most cases, 10 to the whatever power we're talking about. So you're just going to need to put that number there. So on your calculator, you'll have buttons. Let's say we're talking about 321,000. So if we wanted to change this to scientific notation, we know that that would be 3.21 times 10 to the, that's 1, 2, 3, 4, 5. So 3.21 times 10 to the 5. Okay, now the way that we would enter this in our calculator is we would write 3.21, and then we use the EE button. And so typically, or the EXP button. And then we put 5. And so that will give us the same value as this decimal form. Okay. Now, if we're talking about a negative number or a smaller decimal, so let's say we had, let's say we had 0.0000142. So in this case, for it to be scientific notation, we would put 0. I'm sorry, we'd go in this direction. 1, 2, 3, 4 spots. So then we would write it as 1.42 times 10 to the, and since this is a small number, we know that this is going to be a negative. So then that's 1, 2, 3, 4, -4. So the way that we would write that would be 1.42 EE or EXP. So the EE button. And then there's a button that's either, it'll say, in some cases, just parentheses minus. So you don't want to use negative, you know, as in subtraction. You want to use the parentheses minus button. You see. Okay. So you're going to use the parentheses minus button, or sometimes you'll see it, it'll say plus slash minus and parentheses as well. So you'll see it written both ways, depending on the type of calculator you have. And then you want to just put 4. Okay, questions? Okay, good. Okay, now when we talk about quantities, right? Quantities are always going to be a value and a unit. Okay, so for instance, if I tell you guys, I need you guys to do 5, right? Or I'll need you guys here in 5. Okay. So in most cases, you guys are going to sit there and say, does he mean 5 minutes, 5 seconds, 5 hours? So it's important for us to include what the unit is, because otherwise we don't know what we're making reference to. If I just said 5, I need you guys here in 5, that could be 5 days, 5 years, 5 months, So we want to make sure that we always include the unit with the value that we're talking about. So an example is 50 minutes, right? So if I want you guys to express 50 minutes in seconds, what we're going to do is we're going to set it up to make that conversion. So we know that we have 50 minutes. That's our starting. And I know that I want to get to seconds. So that's what I want to go to. So what is the conversion for minutes to seconds? Okay, so we know that for every 1 minute, that's going to be equal to 60 seconds. Okay, so in this case, we're going to do what I refer to as dimensional analysis. I often will call dimensional analysis. So I have minutes, and here I have minutes on top. So minutes is what I'm starting with. And the way I always like looking at things is I like looking at things as importance, right? So things that are more important, I put them on the top of my list. Things that are less important, I put them on the bottom of my list. So in this case, I'm going to put the thing that is most important, right? So in this case, I'm going to put my 1 minute on the bottom because I want to get rid of minutes. It's kind of like if you think about, your old boyfriend and then your new boyfriend, or your old girlfriend and your new girlfriend, right? So my new girlfriend is going to be on top because she's a bigger priority. My old girlfriend is going to be on the bottom because I've been wanting to get rid of her, right? So on top, I'm going to put 60 seconds because that's the one that is a priority. So then in this case, my minutes are going to be able to cancel out. So those units are able to cancel out, and then I'll just be left with seconds. So then I'll just multiply. So this line here, right, is going to represent multiplication. This line here is going to represent division. Okay, so okay. So then in this case, we're just going to go 50 times 60, and that's going to be 300. Okay, questions? Okay, since you guys are very vocal here, I'm going to keep moving forward since that means you guys got a clear understanding.
Sure.
Oops.
There was more corrected.
Oops, I forgot 10. So sorry, 3,000. My bad. Sorry. Come on. So that should have been 3,000, not 300. My bad. Okay. Okay. So the next question, the oldest horse track in the United States is the 8-furlong Pleasantation Fairgrounds racetrack in California. What is the length of the racetrack in rods? 0.025 furlong is equal to 1 rod. Okay, so what I want you guys to do is I want you guys to set it up similar to what I just did with changing minutes to seconds. Okay, so I'm going to give you guys a minute to do that. Okay, sorry about that. As I said, I'm doing a double duty right now. You got to bear with me a little bit. So we always want to start off with what's given to us. So in this case, what's given to us? What are our givens? One of them is going to be a conversion, and then one of them is going to be our starting point. So where are we going to start at? Anyone? Don't you guys all yell at me at once. Okay, so I'll help you out this time. So in this case, we're going to be going with the 8 furlong. So that lets us know what we're starting off with. But we also want to know where we want to go. What is it that we want to get to? And we want to get to the rod. Okay. Good job. Okay, so then we're going to start off with 8 furlong. But okay. And then we have the conversion. We know for every 0.025 furlong, that's going to be equal to 1 rod. Okay. So as we said, we're starting off with furlong and we want to get to rod. So what's going to be on top? You got a 50-50 chance. The rod, that is correct. Okay, so we're going to put that 1 rod on top. And then we're going to put the 0.25 furlongs on the bottom. Okay, so in this case, furlongs are going to cancel out, and we're going to be left with rods. So as I said, this line represents multiplication. So we're going to do 8 times 1, and then this represents division. And then we're going to divide it by 0.025. So let's go ahead and do that. Okay, so that's going to be 320. Okay, questions? No questions? Any concerns? Anybody want to give me $3 million? Oh, yeah, there's a big no for that one. Well, if you guys change your mind, I'm always taking donations. So, okay, so let's go ahead and move forward. Okay, equivalency and conversion factors. So, equivalencies are kind of like what we just did with the furlong and the rod, right? So it's expressions of two different quantities with different units, and they're going to be representing same types of properties. In this case, that was distance, right? And a conversion factor is similar, right? So it's the same thing, it's just different units of measurements expressed for the same quantity, okay? Okay, so write the equivalencies and the conversion factors for the following. 1 day is equal to 24 hours. So is there different ways that we could sit there and say that? And then the other one is my car averages 17 miles per gallon. Okay. Okay, so for the first one, 1 day over 24 hours. Or we could have 24 hours over 1 day. Okay. So same thing down here. We could have 17 miles and MI is the abbreviation for miles, and 1 gallon over 1 gallon. Okay, so when we say per, we typically have 17 miles per 1 gallon. Okay, and we know that we could write that the other way. We could have 1 gallon on top over 17 miles. So the fact that we can flip them, as long as we keep the units with the correct with the correct, as long as we keep the correct value with the right units. So like 24 in hours and 1 in day. Okay. Touch it. Touch it on the side. Is it how warm? Is it like really warm? Is it just like, so that's perfect. Yeah. That's perfect right there. Mm-hmm. That's right.
The two.
So what you want to do is okay, let me finish. Let me get them to the next problem and then I'll show you. Okay, so let's move forward. Sorry about that. Okay, so now what we're going to do is that we're going to calculate the number of weeks in 672 hours. Okay, now we're going to start off with the 672 hours and we're going to end up with the number of weeks. Okay, so I'm going to let you guys start this off and then I'll come back and we'll go through it. Now we're going to start off with our given, which is 672 hours. And our goal is to get to weeks. Okay, so we want to get to weeks. So we're going to put equal weeks. So what are some of our conversions for what type of measurement is this? Is this meters? I mean, is this distance? Is it volume? Is it time? Is it temperature? Is it time? Okay, so what are some of the different time measurements that we have? Yes. So we have days. So how many how many hours are in a day? Okay. And give me another unit. So if you have days, then how many weeks? Okay. So how many days are in a week? Okay. So we have 7 days is going to equal 1 week. Okay. So then we can use these conversions to get to our points to try to get to weeks. So we know that for every 1 day, are we going to put day on top or on the bottom? Since we're trying to get rid of hours. Okay, so we're going to put the day on the top because that's what we want to get to. And we're getting rid of hours, so we're going to put the hours on the bottom. So hours cancel out. That would leave us with days, but we don't want days, so we want to get to weeks. So am I going to put, in this case, am I going to put days on the bottom or am I going to put weeks on the bottom? Okay. Okay, so we're going to go ahead and put days on the bottom. So we're going to have 24, I'm sorry, not 24, 7 days. It's been a long day. 7 days on the bottom, and then 1 week on top. Okay, so then days are going to cancel out, and then we're going to be left with weeks. So again, this line represents multiplication. This line represents division. So we're going to have 672 times 1 times 1. Then we're going to divide it by 24 times 7. Okay, so we know anything times 1 is going to be itself. So then we're going to end up with here. Four weeks. Okay. Questions? Any concerns? Okay. Okay. Let's keep going forward then. Okay. So what is the distance expressed in miles? Will an automobile travel in 3 hours at an average speed of 62 miles per hour? Okay. So I'll give you guys a minute to work the problem, and then we'll go over it together. Yes, and you want to record that value. So it was 1.400 exactly, because that's going to let us know how to calculate our alcohol. Okay, so let's go ahead and get started. Okay, so it says, what is the distance? Okay, so our given, what we're gonna start off with is gonna be our 3 hours. And then our speed is gonna give us our conversion from hours to our speed. So we know that in this case, we're gonna have 1 hour on the bottom because it's per hour. And then we're gonna have 62 miles on top. So, like I said, we're getting rid of the old guy to get to the new one. So we have 186 miles. Okay. Any questions? Yeah, good. Okay. A little girl breaks her piggy bank. Inside, she found 2,006, wait, 2,608 pennies. How many dollars does she have? So our given in this case is going to be 2,608 pennies. And then we're going to divide it by, so we know how many pennies make a dollar. So 100 pennies are going to equal $1. Okay. So in this case, we're going to have dollars on top and pennies on the bottom so that we get rid of our pennies. So we end up with $26.08. Okay. So metric system. So most of the world uses the metric system. We have a tendency of in science, we use the metric system. In the US, on the roads and things to that extent, we typically don't. And there have been a push to try to move everything to the metric system, but it's always uh, it's always faced opposition. And so if you've been to any other country, most other countries use the metric system. And so we're going to be talking about it. And one of the benefits of the metric system is that it's base 10. And it's also decimal base. Okay. We're also going to be talking about SI units. SI units basically stands for the International System of Units or System International. It's the units that we've all kind of agreed to use when we're talking about science and in our fields. And so all of that, or most of them, will be based on the metric system. I'll see you guys on Monday. Yep. So when we talk about the metric system, we're going to have a base unit. So that base unit is it helps getting us established. So we'll be talking about, like, say, for instance, when we're talking about mass, we'll be talking about grams. So grams would be our base unit. Okay. As I said, it's going to be based upon multiples of 10. And so when we talk about a kilo unit, that means kilo is going to represent 1,000. So it's going to be 1,000 times our base unit. So if we're talking about a kilogram, we know a kilogram is going to be 1,000 times greater than a gram. If we talk about deci, so deci is 10 to the minus 10. So it's 10 times less than our base unit. I'm sorry, it's 100. 10 to the minus 2, not 10 to the minus 10. Sorry. Long night again. So 10 to the minus 2. That would be a deci, right? I'm sorry. 10 to the minus 1. I am really off today. 10 to the minus 1 unit, 10 to the minus 2 would be a centi. So we know that would be 10 times less than our base unit. So a decigram would be 10 times less than a gram. And I'll show you this in another table here in a minute. Okay, so this here represents our table. So this is our base unit. So for mass, we have grams. For distance, we have meters. For volume, we have liters. So if we go a deca, that's going to be 10 times greater than our gram. If we go hecto, that's going to be 100 times greater than our gram. As I said, kilo, that's going to be 1,000 times greater than the gram. So a kilogram. Mega is 10 to the 6 times greater, or a million times greater. Giga, 10 to the 9th. Tera, that's going to be 10 to the 12th. When we go the other direction, so this here represents our base units. So if we go 10 times less than our base unit, it's deci. 100 times less than our base unit is centi. 1,000 times less than our base unit is milli. 1,000,000 times less than our base unit is micro, and 10 to the minus 9 is going to be nano, and 10 to the minus 12 is going to be picto. So when we talk about mass, we're going to be talking about the quantity, the measurement of the quantity of matter. When we talk about weight, we're going to be talking about the measurement of the force of gravitational attraction on a body. So we know that when we talk about mass, mass will be independent of gravity, where weight is dependent of gravity. So if I say your mass on the Earth and the moon, are they going to be the same? And in that case, it's going to be the same, yes. But if I say your weight on the Earth and the moon, are they the same? And no, they're not, because the gravitational pull or the gravitational attraction on the moon is less than that of the Earth. Okay. So SI units for mass, length, and volume. So for mass, it's going to be the kilogram. And so we know that 1 kilogram is going to be equal to 1,000 grams. So our base unit is the gram, but the SI unit is kilograms. So that's typically the unit that we use. But really in science, we use the unit that is more appropriate for the weight that we're looking at. So for instance, if we're talking about quantities that are in a single tablet or a pill, we will either use milligrams or micrograms, right? Where if we're talking about quantity of say quantity of a truck that's in a truck, so we'd probably be talking about either kilograms or megagrams or even gigagrams, because it's pretty big, you know, big four-wheel, you know, eight-wheeler. If we're talking about distance, we're going to be talking about meters. Okay. And then again, it's going to be depending on what we're measuring, right? Because we're not going to use a kilometer to measure the length of a caterpillar, right? So more likely we're going to be using either centimeters or millimeters. So this picture is just basically it's a platinum iridium cylinder that's basically used as for calibration. And so this allows us to calibrate 1 kilogram to pounds. So 1 kilogram is going to be equal to 2.2 pounds. So for instance, if I have a Tinder profile and I put on my Tinder profile, I'm 100, right? In terms of my weight. So most people in the US are going to think 100 pounds. And so you're thinking, well, there's this guy, he looks a little chubby. How in the hell is he 100 pounds, right? So you're going to be like, yeah, this guy's lying to me, right? And so we always have to make sure that we're using the appropriate units to help us understand what we're talking about. Where in Europe, if I said I was 100, they would assume it would be kilograms. And so, and that is approximately 220 pounds, which is about what I weigh. So, okay, length. So we're often having to make those conversions, like kind of like with pounds and kilograms. We're going to have to make those conversions from US customary units, which we use pounds, inches, feet, to the metric system. And so we often need to remember those conversions. If you guys pick up a packet, we have packets at Mesa. If you need more of those packets, let me know if there's a shortage. If you happen to be at the Mesas at Lemoore and Coalinga campuses, I'll be putting them there. The ones in Lemoore will be hopefully placed there next week. I tried to put it there today, and unfortunately they weren't in. So we'll get you guys some packets that are there that'll help you with your conversion, and there's also periodic tables. I also have notes that'll be posted there too. So copies of the notes there too. So when we talk about volume, so the SI unit for volume is cubic meters, but often we will use the liters and milliliters. We'll use cubic centimeters. So we know that well, you will know now, 1 cubic centimeter, often we'll say cc, is going to be equal to 1 milliliter. Okay. And we also know that this is cm cubed. Okay, so this is just basically showing us the relationship of a cubic centimeters to one of a cubic uh, to a cubic centimeter relation to a a milliliter and a liter. And so this kind of helps us understand. So when we talk about volume, volume is going to be the space that's being occupied. Okay, so that's like the space that's being occupied by a cube, right? And so hence cubic centimeter. Okay, so we have these unit relationships. So kilo, we know that a kilo is always going to be 1,000 times our base unit. So regardless of whether our unit is milliliters or grams or meters, a kilo is always going to be 1,000 times greater than our base unit. Centi is always going to be 100 times less than our base unit. So if our base unit is 1, that's going to be 100 of that unit. Milli is always going to be 1,000 times less than our base unit. And so we want to make sure that we understand those because those are the most commonly used ones in chemistry. So those are the ones we're going to be talking about quite a bit. Okay. So how many grams are in 0.711 kilograms? Okay. I'm going to give you guys a minute to work that out. Okay. And so we want to get to grams. So we want to use that relationship between grams and kilograms. So we know that from what we just saw, our base unit is grams. So we know that kilo is 1,000 times greater than our base unit. So we know that for every 1,000 kilograms, 1,000 grams, today is a day. For every 1,000 grams, that's going to equal 1 kilogram. So 1 kilogram is going to be 1,000 grams, since we know that a kilo is 1,000 times greater. So those kilos are going to cancel out, and then we're just going to be left with grams. So that's going to be 711 grams. Okay. I'm going to hold it for you. Okay. So we're going to convert 5.25 times 10 to the 5 milligrams to kilograms. I'll give you guys a minute to work through it, then we'll talk about it.
Almost forgot to put these.
Oh, it's most important part. Yep. Okay. So we have 5.25 times 10 to the 5 milligrams. And we want to get to kilograms. So often we may have to do a couple of conversions to get to where we want to go. So we know that for every 1 gram, that's going to be equal to 1,000 milligrams. And then we know for every 1,000 grams, that's going to be equal to 1 kilogram. So we're going to use those conversions. So since milligrams is here, we want to put milligrams on the bottom here. So we're going to go ahead and put our 1,000. Milligrams on the bottom. So then those units are able to cancel out. And 1 gram on top. And then we know, since we have grams here and we want kilograms is our goal, we're going to put 1,000 grams on the bottom. And then 1 kilogram on top. Okay. So those units are going to cancel out. We're going to end up with 5.25 times 10 to the minus 1. And that would be kilograms. Or 0.525 kilograms. Okay, questions? Do you guys have any questions? Any concerns? Anybody want to give me a couple $1 million? So if you don't say no, I take it as yes. So I'll be expecting my money next week. Okay, good question. So how did we end up with -1 on the top? Okay, so we're putting in this case, it's scientific notation, right? So the value is actually 0.525 if you enter your calculator. Enter it by your calculator. So we had this number here, which is 525 times 10 to the 5th power. We're dividing it by 1,000, which is 10 to the 3 power. And then we're also dividing it by another 1,000. Okay. So that's basically 10 to the 6 power. So in other words, we're doing 5.25 times 10 to the 5 over 10 to the 6 power, right? So if we have both being base 10, if we're using division, division is like subtraction. So you're just subtracting the exponent. So in other words, this will be the same thing as saying, oops. $5.25 times 10, 5 to the 5th power minus to the 6th power, right? So that would be the same thing as that. And so then our exponent is going to be, so we still have the same root. And then our exponent, since it's 5 minus 6, is going to be 10 to the minus 1. So it'll be 10 to the minus 1 power. Okay. Okay, good. Okay. A fruit drink is sold in bottles that contain 1,892 milliliters. Express the volume in cubic centimeters and in liters. So in both cases, we know that 1 milliliter well, in the first case, we know that 1 milliliter is going to be equal to 1 cubic centimeter, or cc. So, or we could say cm cubed. Okay. In the other case, we know that 1 milliliter is going to be equal to 1,000. I'm sorry, 1,000 milliliters is going to be equal to 1 liter. So in this case, that's going to be a relatively easy conversion as well too. So first case, we have 192. Well, since they're 1-to-1, we know it's going to be the same value. Only thing, we're just going to use a different unit. 1 mil and 1 cubic centimeter. $1,892. Okay. In the other case, we're going to be dividing it by 1,000. So we know that 1,892 milliliters, it's going to be divided by 1,000 milliliters. So then our milliliters are going to cancel out. And we're going to be left with liters. And it's weird because closed captioning should be on. And so that's going to be 1.892 liters. Okay, questions? Any questions? Okay, let's move on to the next topic. Our next topic is significant figures. Now, when we make reference to significant figures, we're talking about aspect of accuracy. Now, not all pieces of equipment are created equally. So, like for instance, I bought my scale at the flea market, right? And so it's kind of used and everything like that. So it gives me values that are not exact. They're a little bit off. Where one of my best friends, is really wealthy, and he has this specially ordered scale that goes down to like 0.222. So for instance, my scale will give me values like 230 pounds and 220 pounds and 230 pounds. So that's the one that my scale. It doesn't give me anything in the zero column. It just gives me these numbers, right? So my friend's scale, his is like 232.52 or 54, 232.4, and 232.51. Okay. So my friend's scale is more accurate, where my scale is not as accurate, right? And because we'll be taking data in some cases from something that may be more accurate, in some cases that data may be less accurate, we need to find something that's going to be good for both situations. And in science, we often do this. We get data from all over the world, so we have to pay attention to that accuracy. And so we have to take some type of accountability for it. And so what we do to do that, to take account of that uncertainty, like in the case of my measurement compared to my friend's measurement, there's a lot more uncertainty associated with my measurements than my friend's scale. Okay. And so we want to take consideration in both cases. Okay. So what we've done is that we've, rather than always attaching a plus minus to things, we've wrapped it up in terms of significant figures. And so we'll show our data based upon those number of significant figures. And I'll show you what I mean by that here in a minute. So let me see if I can explain it a little differently. Now, when we talk about exact numbers, so things that we know that are absolutely exact, right? So we don't use significant figures. We don't apply it to those things, okay? So if we know that something is exactly this, then we don't apply it. So like, for instance, when we talk about conversions, so most conversions are considered to be exact. So like, for instance, 24 days equals, 24 hours equals 1 day. It's been a long day. 24 hours equals 1 day. So we know that 24 is an exact number, and that 1 day is an exact number. We know that that's exactly. So then we're not going to be using significant figures. Also, in most cases, we do not use conversion factors to determine significant figures. Okay. Now, so I don't want you guys to misunderstand me when I talk about sig figs or significant figures. That doesn't mess with the value. So we're not going to be affecting the estimated value, but what we're going to be affecting is how many non-zero numbers that are going to be present for the most part, or how many non-zeros and those special zero numbers that are going to be significant. And I'll show you what I mean by that here in a second. Oops. So when we talk about sig figs, we have what we call leading zeros. So these zeros here, these zeros are not considered to be significant. They're placeholders. They're placeholders to let us know the value of that number. But here we only have two significant figures. So these values are the values that we're sure about. These values, they're just holding the spot to let us know that this value is a very, very small number, right? And that's the same thing here with these zeros. So these are called leading zeros. They're not considered to be significant. So we don't count them in terms of significant figures. So only these numbers here, non-zero numbers, are going to be considered significant. Now, in the case of lagging zeros, again, they're placeholders. They're there to let us know the value of things. But the non-zero numbers are going to be the significant numbers. Since there's not a decimal point here, right? These numbers aren't considered to be significant. As soon as we put a decimal point after that last zero, those numbers become significant, okay? So they let us know that in that situation, we're sure about these numbers, right? There's no uncertainty associated with them because we took the time, that extra time, to put the decimal point there, okay? But if we don't have that decimal point there, those zeros are non-significant. It doesn't change the value. This is still 12,340,000, okay? And that's going to be important. It's not 1,234. It's going to be 12,340,000. Those zeros are necessary for writing its true value, but they're not significant, okay? And so here we have 5 significant figures. So as we move down, we also have captive zeros. So if we have a zero between two non-zero numbers, that zero is considered to be significant because it's a captive zero. We're sure about it because we're sure about that number following it. Now, these zeros aren't significant. So in this case, we would have 3 significant figures. Okay. And then this one, we have 4 significant figures because we have 2 captive zeros. The following zeros, or the lagging zeros, they're not significant. Okay, now in this case, since we took time to put that decimal there, and then it's followed by zeros, we're making it significant. So in this case, we have 5 significant figures because by nature, we are lazy. If we decide to put that decimal there and put zeros there, we're saying we're sure about those numbers, right? And not only are we sure about those numbers, they're going to be important for you or significant. So we need to make sure to include them. Okay. So, because normally we would just write this as 100, right? So we would write it as just 100 rather than writing it 100.00. By us putting those zeros there, taking an extra time to put the decimal point there and the zero there, that means that they're going to be significant. And so that's the same case here. So in this situation, we have 8 significant figures because we took the time to put the decimal there and follow it up with the zeros. Okay? Are you guys understanding it? You got a grasp? You feeling confident? Okay, so there's 3 of you guys here, right? So this is what we're gonna do. I'm gonna put up 3 numbers, and I want you to tell me how many sig figs they have. And I'm gonna ask you guys to give me your answer. Okay, so let me get a whiteboard real quick. Let's see. Okay, so my first number. Actually, we'll do 5 just to make sure we have a good grasp. Okay, so that's my first number. Actually, we'll just type it. So. Okay. So we're trying to determine the number of significant figures. Okay. So let's start with the first one. Let's see. Chanel. Or sorry, Chanel. Sorry, Chanel. How many sig figs do we have for that very first number? So that 0.02 0.0521. You can put it in the text. Okay, that's correct. We have 3. So the very first one has 3. Okay. Okay. And what about our next one? Let's see. Jocelyn. That's right, 4. Okay, now Lisette. That's right. The next one would be 4. That's right. What do you guys think about the next one? Four, that's correct. And then what about the last one? That's right, 6. Good job. Okay, so you guys have a good grasp of sig figs. Okay, good. Let's see. Okay, so when we start talking about the addition and subtraction of significant figures, what we're going to do is we're going to line things up. Okay, so let's say in the case of the very first number that we have here, we're going to start off by lining up everything, and then we're going to go through each line and determine which one is significant. So let's see, that's one line. So we want to figure out where significant ends for each of the numbers. So for the very first number, significant ends between the 2 and the 0. So we're going to draw a line between that 2 and a 0. And I thought I was going to draw a line between the 2 and the 0. Let's see. Okay, for the second one, it's also between the 3 and the 0. For the third one, I'm going to use a different line, different color line for the third one. It's going to be between the 2 and the 0. And then for the last one, it's going to be between the 1 and the 0. Now, what we're going to do is we're going to take the one that is furthest, the line that is furthest to the left, and that's going to be our deciding point. So then we're going to go ahead and add everything up together. So then if we go ahead and add this up, this is going to be 0. Oops. So that's going to be a 6. That's going to be a 3. And then that's going to be a 2. And then that's going to be 3. Okay. So then what we're going to do is where we have that line that's furthest to the left. So in this case, it's going to be the pink line. So we're going to take the number after that pink line. So we're going to take this number here. Now, if this number is greater than 5, then we're going to round up. If it's less than 5, then we're going to put zeros there following it. So in this case, this number is only going to have 2 significant figures. So it's going to be 32,000. Again, long night. And that's it. Because this value here is a 3. So we're not going to round it up. Instead, we're just going to drop them down to zeros. Okay. Now, if this number is a 5, if this is a 5 exactly, and let's say there's a 0, 0, then in that case, we're still going to leave it as 32.000. If it's greater than 5, let's say it's a 5.2, then that would technically be greater than 5. So in that case, we're going to round it up. Okay. So we're going to do the same thing over here for the next problem. So I'm going to let you guys try to work on that problem. And then we're going to do very similar things with subtraction. Subtraction works exactly the same way. Okay. So I'll give you a minute to work on it, and then I'll come back and we'll talk about the answer. Okay, let's go ahead. So in this case, we have significant figures. It's going to be right there. The next one is going to be right here. The next one is going to be following there. So, and then the last one is going to be right here. Okay, so now that we know where our sig figs are, so for the first one, it's the pink line. For the second one, it's the pink line. For the third one, it's the green line. And then for the fourth one, it's the orange line. So we're going to go the one that is furthest to the left, which is going to be the green line. Oops, there's a question, sorry. Is that not working? Sorry about that. Okay, so no, you're not putting the line anywhere. So you want to put it after you lose significance. So in this case, like in the very first case, these numbers, these leading numbers aren't significant, but significant ends after that one. And then in the next case, you want to put it where significant ends. It also ends after the one. In the third case, the 0.011, significant ends after the one again. So we're going to put a line there. And then in the fourth case, significant ends after the 3. Okay. So then what we're going to do is we're going to go ahead and add them all up, right? Like we did before. And then in this case, so that's going to be 2. That's going to be 1. That's going to be 5. And 6. 1. 0.1. Or 1. Okay. Okay, so 1.0. Okay, so we drew the green line. So that's where significant is going to end. So we're going to take that number that's following it. Let's see. Okay. And we're going to take this number. Now, if this number is 5 and greater, or if it's greater than 5, we're going to round it up. If it's less than 5, we're going to make it a 0 and leave, make everything else after that a 0. And, well, we're not going to even use this. We're not going to use it at all, right? So then in that case, these are only going to be the ones that are going to be significant. Okay? So is this greater than 5? Since there's numbers following it. Or is it less than 5? So we got a 5 and we have numbers following it. Would that be greater than 5? Or less than 5? So if we had 5.12, yes, that's right. It's greater. So since it's greater, we're going to round up, and then we're going to end up with 1.017. And then in this case, we would only have 4 significant figures. Now, the reason why we don't use any of the other numbers is because we're uncertain. We don't have any numbers here, so we're not sure. There could really be numbers there, but we're not sure about it, right? And so there's uncertainty associated with that number, right? And so that kind of defines the rest of the uncertainty. Well, these guys were more exact, right? But then this one becomes uncertain after that 3. And then the same thing here, it becomes uncertain after the 1. But these were exact at this point, but this one wasn't. So you take the one that has the least uncertainty, and that's going to be the one that kind of dictates whether or not we're going to round or leave it alone. Okay? Any questions? Okay, so now we're going to do the same thing down here with subtraction. Okay, we're going to line it up. We're going to determine where uncertainty starts and ends. So in the case of the very first one, we know that uncertainty ends after the 2. So we're going to draw a line after the 2. And then for the second one, uncertainty also ends after the 2. So we're going to draw a line after that 2. Now we know that the 12,000 is more uncertain than the 20,012 because these have non-zero numbers. So we're going to go with the one that's the most to the left. And then when we do the math, we're going to use that to determine whether we're going to round up or leave it alone. So we're going to go ahead and do the math and put in the values. So we know that that's going to be 0. So that's going to be 2. That's going to be 1. And then that's going to be 8. Okay. So in this case, we have a 1 there. Is that greater than 5 or less than 5? Okay, so it's less than. So in this case, the value that we're going to end up with is going to be just 8,000. Okay, so I'm going to let you guys do the next one, and then we'll talk about it. Okay, so the first thing that we're going to do is to do what? Did somebody say draw lines? There we go. Well, sig figs, we're going to look where significant ends. That's right. So where does it end in the first case? After what number? After the 3. That's correct. Okay, and the second number? I mean, this not the second being down here. Where does it end? After the 1. Okay, so then let's go ahead and do the math. So we're going to subtract the values. So that's going to be 3. That's going to be a 4. That's going to be 9. And there's going to be a decimal there. Okay, so then our final value with sig figs is going to be 0.994. Because we take a look at that 3, and it's lower than 5, so we don't round up. So we're going to just leave it as that value. Okay. Okay. So let's move forward. So when we do multiplication and division, you take the number that has the least number of significant figures. So in the case of the very first one, we have this number has how many sig figs? The 0.001. How many sig figs does that have? 1. That's good. Okay. And then we take the other number. How many sig figs does that have? No, it doesn't have 4. Because remember, this 0 is just a placeholder, right? We didn't put a decimal there, so it's not significant. We have 3. That's right. So which number is greater, 1 or 3? 3 is greater. So we want to take the one that has the least numbers. So we're going to take 1 sig fig. So you go ahead and do the math. So 0.001. So that's what? 1, 2, 3. So you got 2.020. Now, we said we're only going to get 1 sig fig. So then the answer is going to be a 2. And that's it. Because 2 would only be 1 significant figure. Okay? Now, here, for division, how many sig figs do we have for this number right here? We have 4. That's correct. So we have 4 sig figs for here. And then here, how many sig figs do we have? This number here. No, it's not 2. Because remember, there we go. It's 3. It's 3 because we took the time to put the decimal there and that 0 following it. Otherwise, we wouldn't do it, right? That means it's important. So that's 1, 2, 3. Okay. So our answer is going to be 3 significant figures because we want to go with the lowest. Okay. So we go ahead and do the math. So we divide this by 10 essentially. So then our answer is going to be 2, 3, 1. And then here, since we have 3 sig figs, we take a look at the 5. So technically the answer is going to be 2, 3, 1, 0, right? That's going to be our answer technically. So, but we're going to take a look at that 5, right? Now it's 5 exactly because what follows it is a 0, right? So in that case, we're not going to round up. We're going to leave this value as 2, 3, 1, and then we're going to put 2 zeros, placeholders. And that's going to be the answer for that. Okay. Because the only time that we will round up is if it's greater than 5. So if there's a number following here, this would be greater than 5. Since there's no number following it, it's not greater than 5. See. Okay. Are there any questions? Now, sig figs are going to be something that you guys are going to be using throughout the entire semester. Yeah, so for the 5, we're just going to put a 0 because we want 3 significant figures, right? Since this one is 3 sig figs, this one is 4. So we want the lowest number of sig figs. So this is going to be 3 sig figs. 1, 2, 3. Okay? That's right. So we just put that 0 there. Okay? Okay, so let me clear. So when we're talking about these measurements, we're talking about those uncertainties. So like for instance, here we have this ruler, right? If you take a look at this ruler, you can't see any of the measurements on the ruler itself. So when we're looking at this, we can't tell what the value is. We know that this here is a meter stick, but we can't really tell exactly where it's at, right? And so as we look a little bit further, we get a little bit more insight, right? For this meter stick. So now we know that this guy it has 60 centimeters. It's between 60 and 70 centimeters. But we also know that it's kind of close to our 60, more closer to our 60 than our 70, right? And so we could make some estimates about what it is, but we would have a lot of uncertainty associated with it. Okay. And then if we got a better ruler or a better yardstick, now we could sit there and get a more accurate result. So in this case, we know that it's between 60 and 70, but now we also know it's like 61, 2, 3, 4. So it's greater than 64, maybe a little bit more over, because we can see that right here, the edge is greater. But we still know that that's uncertain because we don't have the values that are between there. But we can make a better estimate than what we can make with the other yardstick. So now we can get even closer. We can get a better result. So we can break it down. Well, it's 64.12-ish. So it's about 64 point, it says 3, but that looks like 2 to me. Between 2 and 3. But this is going to give us a more reliable result than the one they gave us that we had from the other yardstick, right? So when we talk about sig figs, it's helping us with that uncertainty. Like we weren't so sure about things. We couldn't tell exactly where it was at. So then that's uncertainty. Okay. So how many sig figs are present in the quantities below? 0.109 inches. You guys want to take a guess? How many sig figs do we have here? That's right. We have 3 sig figs. Okay. What about the second number? 0.0025? 2. That is correct. We have 2 sig figs. Okay. We've talked about how to round off. And so this is just to remind you that you need to round. So if it's at 5 exactly, the number that you're using to determine whether you're rounding up or leaving it down, if it's 5 exactly, we're going to leave it alone. We're going to drop it down to 0. If it's greater than 5, we're going to round it up. So like numbers like this. So if we want 3 sig figs, so we're going to take a look at that fourth number, and then we're going to determine whether it's greater than 5 or less than 5. So since it's greater than 5, we're going to round it to 1.43. And if it was less than 5, then we would just leave it as 1.42. Okay. So a student weighs a beaker and 4 different chemicals using different balances. The initial mass and their sums are beaker, 319.5 grams. Chemical A, 20.460 grams. Chemical B, 0.0639 grams. Chemical C, 45.642 grams. Chemical D, 4.173 grams. And the total added all together is going to be 389.8. Let's see. 389.8389 grams. Okay, so what we're going to do is we're going to line it up since this is addition. Okay, so, and then we're going to take that number since they did all of the math for us. So our deciding point is right here, is that 3. So based upon that 3, we're going to either round up or leave it alone and make these zeros. So what zeros, or we're not going to mention them in this case because we want 4 sig figs. Okay, so we know that we line it up. So that determines how many sig figs that we have. And then in this case, in this case, we take that 3, we know it's 3, so then our value is just going to be 389.8 grams with 4 significant figures showing. Okay. Okay. And are there any questions? Okay. Okay, so in this case, we've talked about the multiplication and division already, so you guys should be familiar with this. So if we have a mass of 1.00 liters of gas and 1.43 grams, is 1.436 grams, what is the mass of 0.0573 liters of gas? And we want to determine the number of significant figures. Okay, so we're going to set it up. We know that this is our conversions. So then we have, starting with 0.0573 liters, using this conversion up here, or using these values up here. So we know we have 00 liters, 1.00 liters, and then we have 1.436 grams. So the liters are going to cancel out. So this guy has 4 sig figs, this guy has 4 sig figs, and this guy has 3 sig figs. So what should be my number of sig figs that I have for this problem? Okay, so how many sig figs do we have? What is the lowest number of sig figs for our numbers here? That's right, 3. Okay, so our final answer should have 3 sig figs. Plug it in. So if we plug in our calculator, it's 8.2228. So then we know that we want 3 sig figs. So we're going to use this number, the 8, our second 8, to determine whether we're going to round up or leave it alone. Are we going to round up? Or are we going to just drop it, make them zeros, or drop it? We're going to round up. So then our answer is going to be 0.823. And the units would be grams. Okay. Questions? Okay. Since there's no questions, we'll keep moving forward. No, did I screw up? I sure did. Yes, sorry. I forgot my 0 there. I need to work on plugging my numbers into the calculator. Sorry about that. So there should have been a 0 there. Okay. Let's see, clear. Okay, so these are some of the conversions that you're going to need to be familiar with. I have packets. So if you guys are close to Lemoore or the campus are going to be on campus, I'll be putting them in Mesa or in the library. If Mesa is not open, I'll see if they hold them for the library. Okay. I have about 5 packets that I'll be leaving. And so there'll be the lecture packets and then also the periodic table and those things. And so you want to make sure that you're familiar with them. The more you use them, the more they stick up here. You don't have to memorize them, okay? You're going to have your packet for all the exams except for the final. So at that point, they should be up in your head. Okay, so these are some of the conversions, other conversions that you need to be working with. And so these are the USCS's United States customary system. And so these are some of the units for length, such as feet, inches, yards, and miles. And then for mass, it's often pounds and ounces. And then for volume, we have quarts, fluid ounces, gallons, and of course, like I said, quarts. A soft drink manufacturer is converting from USCS units to the metric units. If a quart bottle initially is to remain the same volume, what number of milliliters should be printed on it? Okay, so you guys are going to use those conversions that we have before. Maybe. Okay, so we know that for volume, 1 gallon is going to be approximately 3.785. And then we know that 1 gallon is going to be equal to 4 quarts. So let's go ahead and use that then. So we know that we're starting off with 1 quart. Okay, so then we have 1 quart. And we know that this is the exact number. So we're not going to worry about sig figs for that. Let's see. There's a question. Yes, you'll be able to pick them up in Lemoore tomorrow. I'll try to drop them off tomorrow morning around 9:30. So if you go after 9:30, you'll be able to pick them up in Lemoore at the library. And Mesa is now located in your Mesa Center is located in the library, but I don't think your director's in this week. So I'll leave it at the front desk. Okay. So we know that 4 quarts is going to be equal to 1 gallon. So I'm just going to use gal as my abbreviation. And then we know that 1 gallon is equal to 3.7, I think it's 85. Let me take a look back. Yeah. And that's liters. And then we know that 1 liter is equal to 1,000 milliliters. So remember that these lines represent multiplication. And then this line represents division. Okay, so go ahead and multiply everything up to the top. So you get so we're going to get 946.25. Okay. Clear? Okay, so I'm gonna go ahead and stop here. We'll pick up temperature tomorrow, next week. So we'll start up here and then we'll start chapter 2. Okay.